So good morning, everybody. Or I just asked the university or department office that whether I can take my mask off officially, okay? But they strongly recommend that the policy of the Ministry of Education requested all the university that the mask cannot be taken off until the first week of March. All right. Oh, this is a very stupid policy. Anyway, you recorded that? Yes. Oh, this is Jesus. All right. Okay. Never mind. All right. Okay. And that's it. And I will take a break around 10:20. Wednesday. Okay. I have an announcement that the TAs will give their TA sessions on Wednesday, 6 o'clock p.m. Okay, classroom here, the same? This room, all right? Because we are going to give homeworks every week, starting from today. So they will give you the homework and the TA sessions for you to understand how to use all the tools and how to do the homeworks. So if you don't have other things to do, in the Wednesday evening, please come over here during the TA session. My advice is that it's very hard to read all the manuals, trust me. Okay, it's better for you to have tutors or those guys who has experience to guide you through all the trouble, because you are asked to design the chip and tape it out in the end of this semester. So it is very important for you to know how to use these tools. Otherwise, you'll be stuck in the middle. All right? Okay, thank you. So here we go. This is the first official lecture of this course. Okay, and today we're going to give you a very easy one. It's an introduction. Basically, we are not going to go to the technical details. I'll just give you a very important background introduction about this course and this business. So why VLSI? Okay, VLSI. So today we're going to cover introduction to VLSI and the design methodology, and everything matters. Okay, particularly important is that economics. Okay, basically it's about money. Why it's so popular? Why it's so hot in recent years? And what is ahead of us in the area of VLSI? Okay, because there are always challenges. Right, the new technology book comes up. For example, the OpenAI, ChatGPT. Does that affect the development of VLSI in the future or not? Okay, whether the engineers can or cannot be replaced by AIs in the future, you never know. Okay, and the last one is the options for digital systems implementation, because as I said in the first course. In the first lecture of this course, that this course is going to cover digital design only. Okay, all the RF design, analog design, mixed signal design will not be covered in this course, because we don't have too much time in this course. Okay, first thing first, what is VLSI and why we need it? All right, and what are the examples that we have in our daily life? Okay, and what is the technology we prefer to realize or implement VLSI. Okay, these are the 4 questions pop up from day one that we know this term. And then we're going to introduce some details about these parts. So what is VLSI? So these words comes from 2 very old and decent professors. Okay, in 1980, when you were not even born yet. Well, I remember because I entered the college in 1980. It's about 42 years ago. And Mead and Conway, 2 professors, they wrote a book about VLSI design. Okay, 42 years ago. And that was the first one. We call that a Bible. Okay, in IC design. So these 2 professors. They propose the idea to use a lot of patterns. They are all geometric patterns. Okay, for example, rectangular, square, okay, round shape, circle, this kind of geometric patterns to represent the circuits, represent the circuits. And that's their contribution, okay? And this is a set, basically that's a set of geometric patterns to represent circuits on silicon. That's their contribution. That's the first book. I still have that book. Okay, and from the viewpoint of circuit engineers, well, the VLSI is a system of circuits. That's all. Okay, it could be analog, it could be digital, it could be mixed signal, it could be RF, never mind. It's just a set, a system of a circuits. That's from the viewpoint of a circuit engineer. It's pretty easy. So the contribution of these two old professors, okay, is very magnificent, as significant, because it is a cornerstone of the development in the last 40 years about IC design. Okay, and what is a VLSI? There are a total of 4 terms. In the very beginning, okay, we only have limited fabrication capability, so we were only about to develop a few gates on the same die, the same silicon. So that's very small. That's why we call it a small-scale integration. 10 gates, that's all. Okay, no big deal. Then, thanks to the development, thanks to the advance of machines and equipments, then the engineers were able to integrate over 10, okay, maybe up to 100 gates on the same silicon. Well, that means something. That means that the one step forward, that's called a medium-scale integration. All right? Then gradually, of course, thanks to the efforts of everybody in this field, then we were able to integrate up to 1,000 gates on the same silicon. Well, it's really hard. If you think about it, but if I give you a homework assignment that asks you to go to the street and buy 1,000 gates, logic gates, and make them work together, and I think half of you will fail in this homework assignment because it's really very tedious and very complicated. All right? And the last one, we have a official name of this one. When the gate number, the whole number is over 1,000, okay, it's called VLSI because it is out of the computation capability of a single human being can do. It's almost impossible. So you need a lot of help from a computer. That's why there is another research research field coming up following this one. It's called a computer-aided design, CAD. So when VLSI become more and more important in its help, so somebody comes to help, it's called the CAD. It is called a computer-aided design. Without a computer, okay, you cannot deal with the analysis and the design over 1,000 gates. It's impossible. So CAD was booming in 80s and 90s last century, okay, because we need help from CAD field to push the development of VLSI. However, we're not going to talk about this software tool in this course. Yeah, on the other hand, we are going to take advantage of the software tool developed by CAD guys in this course, which is called the EDA tool. It's called the EDA tool. And this tool is going to help us to carry out the VLSI design. EDA stands for electronic, okay, design automation. All right? Right now, there are 2 big companies dominates this field. The first one is called Cadence, okay, which is a tool that you're going to study in this course. Okay, it's called Cadence. It covers the Trousseau, a lot of things. And the second one is called the second company is called Synopsys. Okay, this company, they have the tools to synthesize a circuit, okay, based on the Verilog code or VHDL code you wrote. That's another thing. So right now, EDA tool, totally dominated by these two companies. And number 3 is, I think is, I cannot remember its name, okay, but gradually it will be out of market anyway. So EDA tool is very expensive. Okay, the tool that you use in the school is almost free. But if you go to the IC design house, they have to pay about $10 million per license, per user. Just like that's just like the the money you need to pay if you want to use the Windows or Microsoft package officially. You got to pay. So this is not free. Okay, this is not free. But the university is free. So it's better for you to appreciate that we have this kind of tool in the campus. You're not going to have it when you work in the IC design house. So what is the VLSI? Okay, besides the single chip, there are many other ways to realize a system on circuits. So the first one is the FPGA. It is my belief that you use this stuff already when you are a sophomore, because the W department asks you to take a lot of laboratory course. Okay, FPGA is the one that you should be familiar with, right? So basically, FPGA, a single gate on FPGA is equivalent to 7 to 10 transistor, and this is one. And the second, the way to develop an IC is called the cell-based CMOS design. And this is the one that you write a Verilog code or VHDL code, then use a tool provided by Synopsys to synthesize. So this is called a cell-based design. Every single gate is considered equivalent to 4 transistors. And the last one right now is a dinosaur. Okay, it's called a bipolar full custom process. Well, because I'm not sure what kind of material cover in your course, microelectronics, but in my good old days, that we have to study BJT, bipolar junction transistor, and it's too old. Well, it will not be gone, but the market size of a BJT will become smaller and smaller because it's very power hungry, even though that it is a high speed and high power, but the power consumption is too big. So that's why it was considered as a phase-out process. Anyway, okay, if you happen to work in a power electronics IC design house, perhaps you have a chance to use this design process. Okay, the equivalence is that one gate is around 10 transistors. So these are the conversion factors that we use. Why we need it? It's plain and simple. Okay, why we need it? Because the CMOS technology, okay, gives us a very, very attractive feature. That is, the parasitics is extremely small. Okay, no matter you're talking about resistors, capacitors, and even inductors. So because the parasitics are very small, so that the speed is high. So high speed, that's why your CPU goes from megahertz to gigahertz, and could be terahertz in the future, you never know. All right, so it's getting faster and faster. And what even better is that, okay, the power consumption of if you use the CMOS is even lower than before. For example, if you only use a bipolar, well, I'll give you some number, okay? If you use a bipolar to build a CPU, okay, the temperature of that CPU will be as high as lava, over 3,000 degrees of Celsius. So not only you can toast the egg, you can cook a steak, you can hurt yourself, all right? So it's impossible. But however, if you use the CMOS technology, okay, the power assumption will be as low as single watt, maybe microwatt, very small, right? And of course, it's the size, it's physically smaller. So less trip area, that means the cost will go down, right? So everyone loves it. So anyway, everything comes down to one thing and one thing only, about the money. Okay, about the money. Because everybody likes to have a product which is cheaper, faster, okay, less power hungry, okay, and affordable. So the cost goes down. And because we integrate everything on a single die, that means we don't have to go through the trouble to go to factories to the assembly. Or you don't have to bother to go to the SMT factories to put everything together on the board. You save a lot of cost, okay? All right, I'll give you some example. Okay, you heard these names before, okay? Microprocessor, which you use every day. Okay, when you pick up a phone and you talk to your boyfriend or girlfriends over the phone, that means you use the microprocessor already. Okay, and then microcontroller. Microcontroller, if you have a power, if you have a car or a motorcycle, okay, you use the ignition, and or you turn the wheel. That means you take advantage of the microcontroller. And memories, okay, the main memory, the cache, and the flash disk that I use in this course, pen drive as a flash. And the last one is it's called a special purpose processors. Not only we already developed the process to take care of the voice recognition, voice processing. Right now we have another one which I did not put it down. It's called the AI processor already. Okay, a few companies already announced that they have the ASP, AI signal processor. Okay, and this includes several big name companies in Taiwan, for example, MTK, TSMC, excuse me, and maybe Jingtech, I don't know. Okay, they just announced they have it. I don't know whether it's true or not. Anyway, so this is called a special purpose process. The AI era, okay, is coming, and we should be well prepared to welcome its coming. So what is the technology we prefer? Okay, the first one is the one that we prefer. It is called the CMOS. The official name is called complementary metal oxide semiconductor. Let me repeat again. It's a little bit long. Okay, complementary. M stands for metal. O stands for oxide. S stands for the semiconductor. So we make it, because it's too long, we like to use a shorter name, which is called a CMOS. Okay, it's low power, high integration density, all right? And right now, as I said on the board, okay, right now it's a major VLSI technology. When you hear a lot of terms from the TV reports, 1 nanometer, 3 nanometers, they all refer to CMOS technology, not bipolar. They all refer to that. And besides the CMOS technology, okay, everybody likes to have a wireless communication tool, which is a cell phone. So the second, the popular one is silicon germanium. And this is for high frequency, radio frequency IC design, okay? So without this stuff, the CMOS cannot transmit the signal over the air because its power is not high enough. So we need something else to help, okay? It is called silicon germanium. And look at this number. Silicon germanium transistors can operate up to 5 to 10 gigahertz. So that's in the range of radio frequency. So that's the reason why you have a very compact size cell phone, and the voice quality is so good because a lot of engineers stand behind you to give you this kind of product, okay? And combining the bipolar and the CMOS together, it is called the bi-CMOS process, which is very expensive right now. But however, this is the future, okay? This is the future, bi-CMOS. We don't have it in the school because it's too expensive. Okay, silicon germanium, and there are some other new technology. The first one is called the gallium arsenide. Okay, this is for the usage of a higher radio frequency. For example, the satellite transmission. Okay, 6G. So we need a high-speed transistor to carry out that kind of mission. So this kind of transistor, okay, made of gallium arsenide, the frequency could be as high as 100 gigahertz. So anyway, so the criteria for VLSI design, two things. Okay, power efficient, low power, basically. The second is high integration. Okay, high integration. That means the density is high and the area is small. Oh, sorry. Okay, I don't know what happened. Anyway, so I checked last night. I don't know what happened to the slides. Anyway, just to let you know. Well, the red box just comes out of nowhere, but never mind. So this is just a brief introduction. So it's nothing to do with our contents yet. So basically, there are 4 steps to develop the transistor using the existing CMOS process. And this kind of process, because everything was developed in the 2-dimensional coordinates. That's why we call this a planar process. So if you look at from the side view, look at from the side of the transistor. So there are basically 4 steps, something like this. The blank here is called the substrate. Basically, you need to buy a wafer from a certain company. Okay, this is a wafer, like a pizza. Right now, you look at the side view, wafer is a plain, okay, simple silicon. It's called a substrate. Somebody called it a bulk. It's the same name. Some bulk. It's the same name. It's substrate. Then you use a chemical way to develop a very thin layer on top of it. Basically, you need to deposit a thin, very thin layer, and it's given by oxygen gas. This thin layer is called the SiO2, silicon dioxide. Okay, this is very good insulator. So that this is a semiconductor. This is a totally insulator that will totally block the current goes from the top to the bottom. All right, so that's a thin layer. The step number 2, we are going to open a window somewhere that we need. Okay, somewhere we need. So here we are going to use your design, and it's called a mask. Then we are going to take a window over here. This is an empty space. It's not a job. It's not our IC design job. Okay, it's a job of the process engineer. So based on our demand, we like to ask those process engineer or foundry, come on, open the window somewhere. Okay, open the window in the place I ask you to do. Then you coat with the second layer of material. Okay, sometimes it's called the metal. Okay, it's a metal. So this one is called the metal. We deposit the second layer on top of the metal. Metal is a conductor. So metal is required for us to carry signals over this layer. Okay. Then sometimes we don't need this metal layer. We can take away, we can remove them by some certain chemical substance. For example, the acid fluid. Remove it, or we can deposit or implement special, conductive material in the substrate somewhere. So not only we can build a connection, electrical connection over the surface of the die. In the meantime, we are also able to develop the conductive channel under the surface of that substrate. Okay, so that means we can do the connection over the layer or under layer, okay, as long as we need it. So thanks to the help of those process engineers in TSMC, UMC, we are able to develop all kinds of electronic or electrical connections. Okay, there are 4 essential steps. So it's very simple. Their steps can be classified into several categories. Deposition of a certain material, dig a hole, okay, make connections with the different materials, or dig a tunnel, or dig a substrate, a subway, okay, under the surface of a silicon. And it's complicated, but however, we're not going to deal with that. And all we need is to develop those patterns they need and tell them to where we want a connection and where we want to dig a hole. Okay, that's our job as an IC designer. So this is the essential step. We're going to get to more details later. So the IC design methodology, there are 2 ways, basically. The first one is top-down. Top-down is that you are given a spec. You are given a homework assignment. You are given a project description. Then you work from the very high abstraction all the way down to the circuits and transistors and maybe layout. That's top-down. And the second way is the other way around. It's called the bottom-up. So we don't know anything yet. We can develop very high-speed blocks. For example, the adders, multipliers, dividers, okay, ADC converters, this kind of thing. We work all the way up and wait for the signal given by our ranking officers, okay, or project managers. It's bottom up. However, these 2 ways, they all have their own problems. Because for those high-end designers, they don't know about the cost problem. And for those back-end designers, they have no clue about the system requirement. So the best way is that we find out that good design needs top-down and bottom-up efforts together. That means you got to have a capability to understand what the specs demands. Besides that, you are also expected to have the capability to develop all the fundamental modules of this design. So this is the compromise of these two ways. Okay, so the design, we can give you some example for you to understand. So I'll give you over here. Hold on a second. Okay, this is a very interesting design. It is my belief that you all understand what an adder is, right? Because you took the course, the digital system design when you are a freshman, right? And the adder design is a very good example for you to understand why VLSI design is needed. For example, right now, if you are asked by your boss, oh, okay, John and Mary or whatever your name, Peter, right now our company was asked by a big one, which is called MDK, to develop a high-speed 4-bit adder, okay, because they are going to use that in their future CPU or AI processor. Right now, Tom is a project to lead his team to develop this adder. Okay, 4-bit adders is nothing, right? Because when you were a freshman, then you already know that. Okay, I'm going to use. You are already familiar with using K-map and a lot of things to do that. Okay, so because it's a 4-bit adder, So before we go to the 4-bit directly, we are going to use this way 4-bit by 1. We are going to develop 1-bit adder when copied 4 times. Okay, because students like to copy. Okay, or copy the homework, copy the program, this kind of thing, okay, because that's the nature of the students. I did that kind of thing before. Don't be surprised, okay? So then, single bit adder. So now, right now, you use all the tools you learned when you are a freshman. So the 4-bit adder, right now we can assume that we have an AI, A, B, and a C in. We are going to get what? Carry out and sum. Is that right? This is what you learned when you were small, right? And then you develop the truth table. So A, B, C, I. Then you have a total of 8 combinations. Then you are very good in develop this kind of thing. So use your domain knowledge that you know already know that when we find 2 1s in 3, then we gotta have a carry out. Okay, we are going to carry out, and the rest goes to nothing. And for the sum, we can use the exclusive OR. Please don't tell me. Please do not tell me you don't understand this, then we'll be in trouble. So basically, you can develop, okay, a very efficient equation to understand that the C out equal to AB plus BC in plus AC in. Or you already know that this is A, B, right? So then, okay, sir, I already know it. So all I need is is 3 AND gates. We're going to have a C out. Then we need a very big exclusive OR. That's a big one. Then we have a sum. So this is what you learn when you are a freshman. Is that correct? Right? So the next question is that this is a design. For that solution, that's no problem. But right now you are a junior or maybe senior students. The next question will be asked, is this the best or optimal design? Then you're going to think about it again. Is it? Maybe, maybe not. You never know. Okay, so we are going to see how the engineers picture this problem from the viewpoint of the designer. Okay, so you have to throw away all of the design methodology you learned when you were a freshman. So basically, the design process, there are 6 steps to design a given question. The first one is a spec. You got to understand the specs carefully. So the spec, maybe you are a professor, you're an advisor, you're a boss. They don't know nothing about the circuit design. But they are very clear about one thing, what they want. So maybe you are just given a set of requirements. And from time to time, it might not be complete. It might not be complete. For example, in that case, is it complete? Not yet. You never know, because we have not talked about the noise problem yet. All right, then the second thing is behavior. What is behavior? It's over there is a truth table. Because you can use a truth table to describe the behavior you expect in the addition. So model is a set of several programs and much more precise than the spec. Because we have a truth table, we can develop the equations. Equations can be coded as a program. So that's why. Okay, and then the next step is RTL. Now, right now we are stepping in the deep water of hardware. Okay, it is called the RTL level, register transfer level. So we have a Boolean functions over here. See that? We have a set of Boolean functions. We know the input and output over here, right? And we have a problem to understand the delay and area. Because based on the truth-table equation and that gate, gate implementation, we are not going to understand what the delay and area is because it's totally blank. Can you tell what the delay is and what the area is? No. You cannot. It's hardly to be predict if you are given RTL. All right? So the logic is the one on the right-hand side, a structure of gates, registers, and latches. Okay? Perhaps you can picture or forecast about the delay information or the gate count. But in fact, it will not be that precise. I'll give you one example. Okay, why the prediction of a gate delay is not accurate. Okay, right now if you count the delay, I use the C out as an example over here. So right now you say, sir, I was told by my professors when I was a freshman, okay, we have a single gate delay over here, and then we have a two gate delay. It's called a gate delay. Right? It's a gate delay. Right? So you are going to say that, oh, okay, it will be around 2 gate delays. Okay, then you make your statement. But the problem is, are you sure these 2 gate delays the same? Are you sure they are the same? You cannot. I'll give you the reason why. Because this is 2 inputs. This is 3 inputs. Technically speaking, you are going to have a longer one for this OR gate. So this statement or this this conclusion is not accurate. Okay, just roughly speaking, 2 delays, but you don't have the exactly delay information yet. Okay, however, don't panic. We are going to convert the logic gate into the circuits in this course. Okay, then we are going to implement all the gates using transistor. Then you have a clear picture about what's going to happen. Then the next step is that we are going to teach the students to convert the transistor into the layout. Then you are going to have the information very, very close to the real chip. Because when we implement the transistor using the layout, we are going to consider a lot of parasitics. And all these parasitics will be extracted and added in the final simulation of your circuits. Then the delay you found by the EDA tools and these models will be very close to what real world is. So here I'll give you a very short conclusion. The logic is where you stop, what you learn when you are freshman. And in this course, because you are senior and or maybe junior students, okay, you are going to learn all the details in these 2 parts. That will make you different, totally different from the students as a freshman. All right? That's how we make a difference. So we back to the adder design. So the top-down approach is that we do everything from the top to the down, to the bottom. Then we design all the transistors layouts from the bottom to the top. So we are going to combine these 2 strategies together. Okay, so there are a total of 6 steps. This is very fundamental 6 steps for IC designer, okay, for beginners. Spec, behavior, registers, RTL, logic, circuit, and layout. This is where you were when you were a freshman. This is where you are now, okay, for the to learn in this course. So this is a function, description, and there's cost consideration from the bottom to the top. So the spec, okay, could be English, could be French, could be Russian, you never know. Anyway, it's just a piece of the statement. Then you develop program, you develop sequential machines, okay? Then you develop gates, then transistors and patterns, geometric patterns or rectangles. And for the bottom up, okay, you take a lot of things into consideration. The cost does not mean just the money. It's about the areas, which will be described as a microns on the silicon. Then you will be worried about how fast the circuit is. So you are going to explore all the possibility to generate the fastest speed of the circuits. Then we talk about the logic depths, clocks, and the design times or throughputs. Okay, so the power, area, speed, okay, everything is considered not just the design parameters. They are considered the cost of everything. Okay, this is design abstraction. Okay, now let's go to the hierarchy design. So right now, you are working with a very cold-blooded engineer manager. So not only he asks you to do the adder design, he wants you to design an adder which can carry out 3 operands, not 2, 3. So what's going to happen? Okay, one way to do that is, this is one. Okay, I designed the adders which can take care of the addition of 2 operands. Okay, not 3, but I do the addition twice. All right, that's one thing. The other thing is that the other way is that you can use the CSA that you learned when you in the first year of your college, carry safe addition. But we're not going to talk about it yet. So this is the one. Oh, okay. Right now we go to the traditional way. We develop a single adder, and we duplicate it. Then we carry out the addition twice. Then we can get the result that my boss needs. Okay, this is just an example. 3 operands. Okay, that means 2 adders are needed. So let's go to the detail of a single adder. This is a single adder, right? This is the simplest one. It is called a repo carry adder. Repo carry adder is that after we design and fabricate the 1-bit adder, which is simplifies the box over here. Okay, we take 2 numbers. Okay, 2 operands. And number 3 comes from the right-hand side, which is the carry in. Then we're going to deliver some and carry out to the next stage, okay, and all the way up to the end, all the way to the left. So the carry out generation looks like a repo in the lake. So it's called the repo carry adder, RCA. And this kind of adder is very simple because all we need is to design a single adder, then we cascade them together, then the good things happen. But the problem is simplicity, okay, sacrifice what? Sacrifice the speed. It's simple, but it's slow. Why? Because the addition is not done, okay, until we have the final C out, right? So we have to wait a long, long time to get the final C out from the left-hand side. So the delay of this kind of design is just too long. So this kind of design only exists in the textbook example. This is not going to be used in reality, all right? Anyway, I'll give you an example to understand how to do that. So this is a single bit adder, okay, and this is the one over here. So no question, no problem at all. Now the question right now is that what is a circuit inside a single box? Is that a good one over there? Okay, that's the one you learn, okay, when you were a kid. Now let's check the new design. Okay, this is something that you're going to love it. Okay? You say, sir, it does not look like the one over there. But it is the adder which has the same function to carry out that truth table. Okay? And why we need it, why we like to use it instead of that one. Let me tell you why. Okay, you check the sum. See, we have two inputs to the exclusive, then goes to the next exclusive and carry out the final exclusive function. So according to the feature of exclusive OR, it is the same as the exclusive over there, the sum. See, the same. Okay, the same thing happened to carry out. We checked whether both of these inputs operands they are all high or not. If it is high, then we have a carry out already, right? Because if we have both inputs are high, of course we're going to have a carry out high. So we don't have to worry about the carry in right now. So the thing is, if they are not, this will be 0. Then we check over here. If one of them is high, then this output goes over here to end with the C in. If this C in is high and this is high, we're going to have a C carry out again. Okay? And it's coupled to the output. So two cases. Okay? There are two cases. Either both operands are high, or one of them is high, but and the C in is high. In either case, we're going to have a C out equal to high. That's all, nothing else. So we are going to have this design. Why we need it? Why we like it? Because we are going to design, okay, this box once, then we copy it. Because these two boxes, they are identical. So we don't have to worry to redo all the design. The second thing is all the inputs, they are, all the gates, okay, I'm sorry, all the gates, they are two inputs on the same. All the gates, they are two inputs. See, two inputs. And here, you have three inputs. You have three inputs. So in that scenario, we only design simplest gate. Two inputs, that's all. Okay, but in this case, we're not. We are going to design complex gates. And in this case, they are duplicable. So this is one. So as I said, what you learn in the first of your college life is a solution, but it might not be an optimal one. Okay, right now we show you that it could be the suboptimal one, because not only the speed will be better, and the design effort is less. Okay, we are going to use this all the way in our error design in the future. Okay, this is another design. Okay, you don't have to worry about it. It's different from the gate level. So some other experts or some other sophisticated and experienced engineers, they just skip the gate level part. They directly go to the transistor level. Okay, for example, in this one, you see that this is not the gate equivalent circuits. Okay, this is totally different. Okay, we're not going to discuss the detail. In these circuits, the designer take everything into consideration. Okay, using the simplification and minimization of the gate counts. So you can see this one. This is symmetrical. It's over here. And we are going to have a C out. This is C in, and the inverter goes over here. So this is a C in over here, and then this one goes to this way and get the sum. So don't worry about it. I know it's out of your head at this moment. Don't worry about it. This is the one. It's called the Manchester adder design. And we are going to cover it when we are going to discuss the adder design. I think in the middle of this semester, right? This is a design example, okay? The designer directly take the equations into his or her hand and simplified it. Okay, so don't worry about it. And then I just give you an example. Then this is the one called layout. Okay, so after the designer developed his own transistor level, then he uses his knowledge to convert that schematic circuit design into this one. So, and a lot of label you can see over here. This is X in X1, Y1, C in 1, C out, bar, this kind of thing. And this is called the layout. Okay, right now it is still a maze to you. But I'll let you know the design. I'll give you some, some observations that we should learn. See that they use the minimum number of tracks. These are called the tracks. Minimum number of tracks. The less number of tracks you use, the smaller the area. When we do the layout, we like what? We like have a smaller area. Okay, the smaller your design is, the faster speed you're going to get. Okay, and the less parasitic you're going to get. So a lot of advantage of that. So this designer, okay, he used the knowledge that he learned or she learned to minimize the tracks that he needs to carry out that adder function. All right? Okay, this is one. And the second thing is that you can find out that the VSS stands for the ground. And here the VDD stands for the power. So all the transistors, they share the same ground and the same power supply. All right? That makes sure the VDD that they use is the same. That means that the ground they use is the same. So there will be no this power problem. And then the next thing that we observe is that, okay, all the input circuits get into from the left side or the bottom. And the outputs goes to the other way, goes to the other side, it's the right-hand side. So that will be very convenient for us to what? To cascade them together. Right now, if we want to cascade 4 adders together, we don't have to redesign everyone. Okay, we just cascaded this layout together. Okay, the input, okay, comes from the left, and the right, the output comes gets out from the right. Then we copy the same box to the next one. Then we short circuit the output of the first one to the input of the next one. Then we are going to have what? 2 bit adders. They are sitting together. Then we can do the same thing all the way down to have a long adders. Okay, this is a hierarchy design. So a lot of things we can learn from this. We are going to give you more layout example. Of course, the TA, your 2 TAs, they are already experienced students who carry out many designs in IC. So right now we give you a simple one. This is a very simple one. This is called the NAND gate. NAND gate. Okay, I'm going to show you why.